I know everybody looks forward to my quizzes. The highlights of your bi-weekly schedule. It's almost as good as the paycheck, right? Question?
It's the last quiz, right?
It is the last quiz, yes.
I'm gonna be so sad.
I know, right? But you do have the exam to look forward to.
Oh.
So, there you go. But after that, man, you'll just have to get another course with me.
Are you, what other courses are you teaching? Okay, tell me on.
Who knows, yeah. See, at the moment, the only third-year course that might be possible for me to teach is like the third-year course version of this course, which is anti-requisite with this. So, I don't know. There aren't that many third-year Tron courses, to be honest. It depends. Like a lot of the teaching I do is also in the comp sci stream, so we'll see. I don't know. Like it depends on a lot of things. It depends on like what. It depends on what courses are available in the semester that I apply for. Like I'm a sessional. I still don't know what I'm teaching over the summer, right? I usually only find out I'm teaching the course like 2 or 3 weeks before it starts. So we'll see. We'll see how it goes. But
what about 3TG4?
Dr. Down is teaching it and has been teaching it for a while. Unless he's on sabbatical, I imagine he will be continuing to teach it. Dr. Down's a really nice guy. Just like a really warm-hearted guy. So, you're in very capable hands with him. But yeah, At any rate, so we should talk about our actual. You're here. Awesome, excellent. So let's continue where we left off, shall we? So we've been taking this this brief discourse, somewhat brief discourse, into the design of application-specific controllers, right, or single-purpose controllers. We've gone over elements of digital design and the design of combinational circuits, which I got the impression pretty strongly that you guys have done pretty well previously. I got the impression that you guys have done sequential components to a lesser degree. Is that correct? Like in the course that you had previously? Okay. So the advantage, the nice thing about designing controllers with sequential components is that you can essentially break them down in terms of combinational circuits, so long as you include in that combinational circuit those inputs that the state holding elements are expecting, right? So this is going to become, this is going to become more important as we keep going through this. But some important things to remember as we go through the sequence of examples we're about to do. Multiplexer, first of all, properly spelled with an E, not an O before the R, but okay. Requires a selector signal, right? Multiplexers are often used to funnel the correct input into either a register or some kind of, adder or subtractor or comparator block, some other circuit, right? A selector signal is required for that. One of the things that we're going to develop during this lecture is the separation between the data path logic and the control logic. So the data path logic, obviously, the type of stuff we've been talking about so far. The control logic is essentially all of the stuff that we've assumed to have just happened up to now. So selector signal, for multiplexer is going to be important. Aside from that, we already talked about these last class, so let's move swiftly onward. Sequential components. So we have talked about registers at some length. It is important also when you're speaking about a register, to understand that in addition to its clock signal, a register properly instantiated that's not like just a bunch of flip-flops will also have load and clear inputs. Essentially, if you write load, then this functions roughly as an incoming rising edge on the clock did in previous examples. It triggers this register to load whatever is being input into it and actually store it, right? So you're loading the input that's being given. Clear obviously resets the internal state of the register. So it's kind of like a set reset, but applied to everything at once. Make sense? Good. Shift registers, we actually talked about those way back at the beginning of the term. So I won't dwell too heavily on them. And of course, we also have counters. Counters are, of course, very similar to registers. They just automatically tick up, right? Good. Any questions so far? Good. So, let us examine a case study in logic design. Problem description. You want to construct a clock divider. Slow down your pre-existing clock so that you can output 1 every 4 clock cycles. We may consider this a fixed prescaler. So this would be basically the guts of the prescaler module of the real-time clock, not the real-time clock. The timer module from earlier in the course, right? We had that prescaler module. We're going to explore what the logic inside of that thing actually would look like. But we're also going to simplify it so that, rather than have, 8 16 bits inside of that prescaler value register, we will have 2 bits inside of that register, and therefore only have to deal with, the prescaler value will be fixed at 4, but we have a counter register inside of the prescaler that is counting between these 4 different values, up to 3, starting at 0. So, examining the state diagram, right? So, with A being the incoming clock signal, and X being the output of the whole darn thing, you'll notice that we go circularly between these 4 different states, 0, 1, 2, and 3. Note that we transition from 0 to 1 when A is equal to 1 in all cases, and we loop back into the same state when A is equal to 0, also in all cases, right? So essentially, we're assuming that A here is going to have something like a regular clock signal, right? And that we will be oscillating, like basically this thing's going to pick up both the lows and the highs, right? There are certain assumptions baked into this design. We are assuming things about what the A signal looks like. We're assuming that it's oscillating between high and low states, which of course, if we were to, if we were to take just the regular clock signal that was powering the, whatever, we wouldn't see these, right? We would be always performing our calculations on rising clock edges. So this thing has already at least been scaled down by a factor of 2, right? Anyway, so in terms of our output, X is equal to 1 when we reach the state 3 and 0 otherwise. if we take that and we turn it into some combinational logic, first of all, since we are storing values up to 3 from 0, we will obviously be using 2 bits to store that. In this particular example, they have chosen to represent both of those counting bits separately, which allows us to simplify, like it allows us to express things in pure gate logic once we get there, right? We're not going to be dealing with adders or anything at that high a level. We can just deal with gates. That being said, obviously there are some drawbacks to this design. If you're encoding only 2 bits, obviously, you can't go any further than that, right? But this will be fine for the purpose that it is, right? Again, we're not designing a general purpose component. We are designing a single purpose component, and that single purpose is to downscale a clock signal by a factor of 4, specifically. So, if we take a look at the states that we would have, with respect to the state register, we have inputs I1 and I0, and outputs Q1 and Q0 corresponding to those 2 bits that are being stored inside of the state holding elements of this design. So I1 and I0 are outputs of the combinational logic component, right? Although they are inputs here, they are outputs over there, and vice versa. So the existing states in the state register are being fed in. We'll call them Q1 and Q0. Right? Make sense? So far, so good? So, from here, the next step is to design the combinational logic circuit itself. So let's do that. It's another one of my famous pull out my notebook moments. So let's deal first with the output I1, right? If we represent this in sort of the I don't know what you call this, table with a tag, with a whatever you call it. We're going to do Karnaugh map. Just immediately jump into the Karnaugh map, not mess around. Gray coding, very important. So when our inputs are 0, 0, 0, what's our output for I1? Zero, zero, zero.
Zero.
Zero, thank you. What about when A equals 1? Come on, guys.
0.
When Q0 is 1 and A is 0 and the other one is 0 too.
0. 1. 1. 1. 1. 0.
Are we sure about that?
I don't know. No, oh, sorry. It's because I forgot you switched the, yeah, those should be the other way around.
Yeah, there we go. So, groupings. What are our groupings here? Well, we got one here. We got that one. And we got one here as well. So here's a question. Why would we design with an overlap here? Anybody got an idea? Yeah.
Because the larger the section, the fewer requirements you have to have, and it doesn't matter if you can get the same result twice, so it makes sense to have the fewest requirements possible.
Right. So if we were to specify just this guy, right? If we were to draw it like, this, and then that, in terms of the logic, the sub-logic circuits, these guys require 3 inputs. These guys require 2 inputs, right? So you still need 3 components in total, but if you blend it across like that, this guy can be represented with 2 inputs, which makes the underlying logic gate itself slightly simpler, right? So it's actually a good approximation thing, right? Where's my eraser? Eraser. So, zup. So if we take that and we derive a minimized equation for that, first term, Q1 naught, Q0 A, or, what's this one?
Q1A0.
Q1A naught. Say naught, not 0, because 0 gets confused with subscripts, particularly in this example. What about the next one? It's
Not Q2. Wait, yeah. And Q1.
Yeah.
Not Q2.
0, but yeah. So
Oh,
Q1,
sorry, Q0.
not Q0. So there's our minimized output equation for this guy, right? So you take that process, wash, rinse, repeat for the other 2. You end up with the following equations. That's a little small. Do you want me to, I'll blow it up a little bit. Get out of here, you. Quit. There we go. All right, that might be a little bit better, eh? So, taking the state table, translating it into Karnaugh map form, deriving minimized output equations, we get I0 is equal to Q0 A naught and Q0 naught A, or Q0 naught A. And in the case of the output itself is of course only equal to 1 when the state is equal to 3, which is 1, 1, so bing, bang, boom. Both bits and together, and that's what you get. If you take that, put it out forward into actual logic gates, you derive the following circuit. Right? Just an AND gate, the OR of 3 guys for I1, the OR of 2 guys for I0. Now, this is not although these are minimized equations, these are not guaranteed to be minimized circuits. It is definitely possible that there could be further simplifications that could be made here, right? But, good enough for now. Yeah? Any questions? So far as it goes. So now, let us examine the problem of data path versus control flow. So I would like to, once again, we should cast our minds back to the bit at the beginning of the course when we talked about general purpose processors. You remember how inside of the CPU we had the control circuit, we had control, and then we had the ALU, and then we had like memory off to the side. You guys remember that, I hope? So The arithmetic logic unit, just to remind ourselves, performs all of those little manipulations that we saw in the previous example. It's arithmetic and logic, right? The memory is stored elsewhere. In our case, we have registers inside of the data path unit. So between the memory and the arithmetic and logic side, that constitutes the data path, right? Because, well, that's the path that data takes, right? It takes the data itself, starts off stored in memory, is loaded into the ALU, is operated on, and then stored back in memory, right? That's the path of the data. The control unit does all of those little operations which select which memory gets loaded, which operations are performed, in what order. In addition, the control unit, at least in the case of general purpose processors, fetches and decodes instructions from instruction memory as well. It has to, because it's the thing that actually tells the ALU what to perform. So in order to tell the ALU what to perform, it has to know itself, and it gets that by looking up instruction memory. Make sense? Hopefully this makes sense. I mean, you know, if it didn't, if this wasn't correct, then your phones wouldn't work. So, you know, anyway. So with respect to the controller will have control inputs and control outputs that aren't related to the data path, right? Like, for example, control inputs might be instructions derived from instruction memory in the case of a general purpose processor. In the case of a single purpose processor, you may be talking about something like a reset button, right? An incoming signal which has an effect on the manner in which that circuit needs to be controlled. It's an input to the behavior, right? If that makes sense. So with respect to the data path may also have external data inputs that come into it. Anybody want to take a guess what an external data path input might look like? Yeah?
A result from ADC converter, maybe.
Sure, a result from an ADC converter. Excellent example. So, like, maybe you're making an audio recorder, and that's the that's the signal from your microphone, right? There's no reason why that type of data would need to pass through the controller, right? The controller is going to be it doesn't affect which operations will take place, right? It affects the resulting file that gets stored or something like that, right? The example that I had in my brain would be something like a temperature sensor or a light sensor, you know, like a photoresistor, something like that. But like you're generally thinking like switches and knobs and sensors of other types, right? So what would external control outputs look like? Anybody got an idea? Yes? Well, maybe. If this was a controller that was hooked up to another controller, and you wanted to trigger an interrupt when a certain event happened, yeah. So if we think about the timer peripherals in this context, the interrupts that they generate would be external control outputs from the perspective of the timer module. So yeah, absolutely. So we can we can take that idea of interrupts, combine it with maybe we have a status indicator LED, right? You know, on old hard drives, how you had like an LED that would blink whenever the hard drive was being used, stuff like that. Status indicating elements, right? Those would be generated from the control apparatus. So what would external data outputs look like in this context, do you think? What kind of thing would be an external data output? Yeah? Sure, an LCD screen displays data. I would say that like LCD screens will probably also display the current state of the controller, so I would actually be comfortable putting LCD across both of these, right? But yeah, LCD screens, sure. Something like a speaker, right? Something like a, you know, a motor even, maybe. Well, maybe. It depends on how it's being hooked up. But essentially anything where some value that's being stored in the memory would be sent out somewhere to do some job, right? You might, you know, this might be hooking into a digital to analog converter, and God only knows what it's doing from there, right? So good. So this is roughly the division that we set up. So the question kind of becomes, how does the controller actually control what's going on inside of the ALU? Well, I kind of hinted at it earlier. It's controlling such things as the selector signal on multiplexers, and it's controlling such things as the load and clear operations on registers, right? So all of these operations need to be coordinated, right? In the previous example, we kind of just assumed that values were being stored automatically, like once every clock cycle, right? Oh yeah, I just had, you ever have one of those moments with these things where like a piece of fuzz off the back of the mask gets in your mouth, but it's too far back for you to be able to get it, so you just have to swallow it? That's what just happened to me right now. I will be very happy when I don't have to wear these things anymore. Anyway, it's like, well, why are you using one of those cheap disposable ones instead of those nice fabric ones that your wife made you at the beginning of the pandemic, like you were earlier in the semester? And it's like, don't even talk to me. Because we lost them, and then we found them again, but now I have a box of the things, you know? That's why. Anyway, so let's talk about another example then. Greatest common divisor. So, the greatest common divisor of two numbers is that the largest number which evenly divides both of them. It's kind of an interesting. Did I give you greatest common divisor in 2MP3? I think I did. Yeah. Did I have you do it in assembly? Yeah. There we go. So you guys should already be familiar with the algorithm. This is one implementation of it in C, which has been modified with the signals that would be received if we viewed a GBC module in sort of a black box way. So let's imagine that we have a greatest common divisor hardware module that we're designing, 3 inputs, an enable or go input, an X and a Y input. The underscore I indicates input. And then we have D, which stands for divisor, which is our sole output. So, the greatest common divisor algorithm, as expressed in the C programming language, we declare our variables, we have a infinite loop, we have a loop at the beginning which is waiting for the go signal, right? While not go, that will catch execution so long as the go signal has not been received, and it does that every time it iterates the big loop, so it'll catch that every time. We then take two memory holding elements, the ones referenced up here, we assign the inputs into them. This is not usually necessary, but it is necessary in this case because we want to modify those as we go through the algorithm. Also, it's not a bad idea in general to register your inputs, because by registering your inputs when you receive a start signal, you no longer have to trust that whatever is providing those inputs remains stable for the duration of the calculation. So it uses a little bit more memory, but it's not a bad idea in terms of like design stability, if that makes sense. It depends on how much you trust the people you're working with, really. And the answer to that question is you always trust them more than is wise. So there's another, you can put that on, whoever did the Sigma grind set video, you can put that one on there. So the algorithm itself, right, while x and y are different, if x is less than y, then we subtract x from y. Otherwise, we subtract y from x. So it's kind of cool, right? Because like it actually works. I'm just going to demonstrate it quickly. So let's say you had, 12 and 50, right? So subtract 12 from 50, you get 38. Subtract 12 from 38, you get 26. Subtract 12 from 26, you get 14. Subtract 12 from 14, you get 2. Is that the greatest common divisor? Yep, because then it's just like 10, 8, 6, 4, 2. That's a match, right? So not necessarily the most efficient algorithm for calculating greatest common divisor, but it does work, right? So, good. We take this, we compute, or we convert it to what's known as a finite state machine with data path diagram. So this is distinct from the finite state machines we've dealt with so far because it indicates the data path as well. And you can see that this thing is like essentially the structure of the C program, but in a flowchart form. So you can use, like there are programs you can use to generate these, but so you can see the while not go I loop is this loop right here. You exit it, you get these two assignment statements, you then enter another loop, you make a decision, you do that, etc., and then you loop back to the top. That's the structure of the program, right? Good. So, just to go through the components, like specifically, these guys are statements, right? Just like a block is a statement. If it has something in it, then it is a statement. Otherwise, it's a jump instruction, basically. While condition with the loop body statements, then next statement, we have the beginning of the condition, we have the loop body statements, then we have a jump back up to the top, and then we continue. And in the case of branch statements, we have our header state, we have our conditional entrance into one of many states, and then all at the end we collect back into one state again, and then jump again to execution further in the program. It's like, in this diagram you see a lot of boxes with nothing written inside of them. The correct thing to think about those is as assembly jump instructions, right? Or at least that's a better way to think about them than as just blank boxes. Because they are doing something. They're moving around. That's what they're doing. So, good. Excellent. Wonderful. So how do we take this and convert it into our data path, right? Let's talk about the data path first. So, first step, obviously any variables that are in the program must be held as registers inside of our data path. That much should be obvious, right? We also need function units for every arithmetic operator. So you remember how like there was an adder block that we talked about and then we didn't talk about any other arithmetic operations? We're just going to assume that we talked about them. So operations like subtraction, operations like comparison, and not equals. These are all operations, right? This view of data path design, it's like bottom-up construction of the arithmetic logic unit using only those operations that are actually used, right? So no other operations are used than these, right? So can anybody think of a simplification that can be made here? Can anybody pick out an optimization that we could make, even just examining things at this point in the diagram? Yes, sir?
Could you get rid of the subtract box and make it one subtract box?
You could, yes. So we have subtraction repeated here, right? If you look at the way in which it's been wired, right? One subtractor is performing x minus y, the other is performing y minus x, right? X, y, x, y, and you can see that this one feeds exclusively into the multiplexer feeding the x. We haven't talked about the multiplexer yet, but that's a multiplexer. It feeds into the multiplexer, which feeds the x register, and the y feeds into the multiplexer feeding the y register, right? So the direction in which these bad boys are being assigned has been encoded into the manner in which the wires have been hooked up, right? But that doesn't necessarily have to be the case, right? That's been hardwired in, but if we were to throw a few extra multiplexers in there, multiplexers are not overly complicated components, at least not compared to subtractors, we could easily design the circuit such that this input was either x or y based on a selection. This would be x or y based on a selection, and it would feed into one of these two guys based on selection as well. I believe when you go from 1 to 2 possibly, that's called a deplexer or something like that. I don't know, there's a name for it, but it's an inverse multiplexer. But anyway, so that's our sort of starting point, right? And you can see that in every case, the actual operations that are being performed on these guys they've been hardwired in, right? In the case of this guy, at least, we did talk about the comparison unit, and basically this would just be a comparison unit with the less than line fixed and used, and the other lines not used. So yeah, in addition to that, we also have the D output register, which is being picked from the X line here. It doesn't actually matter, right? Once you have determined that they're both equal, obviously you can pick either of them and use that as your output, right? But yeah. Any questions about that so far? Yes, sir.
So would an ALU have a bunch of different subtractors and adders and stuff inside it, and a multiplexer that would kind of decide what operation it's doing?
You mean in a general purpose
Yeah.
processor? Yeah, that's exactly what it is.
Okay. So
Yeah.
how many basic operations are there? Like I remember when we did assembly at 2MP3, to do division, we had to do repeated subtraction.
Yeah, we only had to do that because the particular emulator we were using didn't support that operation. So I'm so glad you asked this question because it's a very interesting question. So for the purposes of the recording, the question is, so what operations are actually in the ALU, right? Given that the ALU is made of these operation blocks and multiplexers, what are these actual operations? And the answer is, roughly speaking, with a couple of exceptions, the instructions of your assembly language. Right? It's not quite a one-to-one because there are some memory operations like load and store which would not need the ALU, right? Like if you're loading from external memory into one of the registers, that doesn't require a ALU operation, right? But like add s, sub s, all of these operations, anything that's not just moving memory around will be a specific module inside the ALU.
So that's kind of where the instruction set comes from then?
That is precisely the case, yes. That is where, it's like when you design the instruction set, what you are designing is which of these modules you want in your ALU, right? So, and that's, like, you can imagine, the more of these little guys, I was about to use a dirty word, the more of these guys that you include in an ALU, the bigger the multiplexers have to be, right? Because they have to feed more things, right? It just makes the circuit larger. So that's why you have the difference between the M4 and the M3 and the M2 and the M1 and the M0. The M0 has the fewest, right? Which means it's the smallest chip, right? Which means that it's also a lower power chip because any circuit you put down requires power to, well, power it, right? So, yeah. Make sense?
So it would have like it would have its own circuit for add, subtract, division, everything?
Oh
It
yeah.
would have its own, okay.
Yeah. And most of those would not have internal state, right? So you remember in 2MP3 when we talked about bitwise operations? You remember how like we did adding like just regular addition but with bitwise? The reason for bitwise is that it's basically logic gates, right? Like that, like if you take a logic gate function and you apply it to two numbers, all of the bits in them sequentially, that's what a bitwise that's what a bitwise operator is, right? So, roughly speaking, the manner in which you perform something like addition using bitwise operations has a reasonably direct correspondence to the hardware which would implement such a function.
Right.
Awesome. Any other questions? Those are good questions. Good. All right, got a few more minutes. So one other thing before we move on from this slide. Notice the lines coming in, right? X selector, Y selector, X load, Y load, D load, right? These guys, the comparison functions, notice that they're outputting to the control module because they are used to control execution, right? In order to know which of these two subtractors are, in order to know which of these two output signals you want to load into these guys, right, you need to know the results of this block, so it must be output to the control circuit. So, good. So, in that sense, we can take this program and we can rewrite it so that instead of, saying y is equal to y minus x, we can say y selector equals 1, y load equals 1. So we can rewrite these operations in terms of the control signals necessary to execute them. Once we have done that, we have a controller. Does that make sense? Question?
I just had a question about that. So for the X selector, Y selector, and all that, so are those controller inputs, or what are those?
Okay, so these are n-bit multiplexers, 2-to-1 multiplexers, right? The selector signal selects which of these two signals gets propagated to this signal, right? And then that signal can be loaded into the register.
Okay. So where do they come from? Like, do they come from the controller?
Yes.
Okay.
Yeah, yeah, they originate in the controller itself, right? So, now that we have a program like this, let me just skip ahead a couple of slides. I know this is like a big wall of ones and zeros, but from the previous description, we can derive state tables which determine which outputs from the control module are set at what time, and which inputs to the control module are set at what time. Right? So from this, we can actually also derive combinational circuitry. Right? Sometimes the controller requires its own state registers as well. See the program counter, right? The program counter would be, like, its purpose is control. So it's related to the controller, obviously. But you know, since we're essentially hard coding a program here, there's no instruction memory, so there's no need for a program counter. Question?
What exactly do the asterisks mean in this case?
Don't care values. Yeah. So anywhere you see asterisks or possibly the X's as well, it's like, don't care what's coming in, don't care what's going out. Make sense? Any other questions? Excellent. We'll see you tomorrow then. Take her easy, folks.